What's up, guys? Welcome back. Today we're going to be starting Combinatorics. It has been many people have asked me personally to upload some Combinatorics videos. Please ignore the noise in the background. But okay, so let's start off with the multiplication rule. The multiplication rule says in a k-step operation, if there are n ways, that just means some natural number of ways, right, to do the first step, and n2 ways to do the next step, and nk ways to do the kth step. The k step would be the last step in the operation because it's a k step operation, right? K is also just some natural number. If there are nk ways to do the kth step, then the total number of ways, oh, by the way, this is dot all the way up to k ways, nk ways. Then the total number of possible ways of doing the operation is n1 times n2 times n3 times dot all the way up to nk ways. So what that means is, if we have, let's say, operation, 5-step operation, and there are, let's say, 3 ways of doing the first one, 4 ways of doing the second one, 6 ways of doing that one, 2 ways of doing that step, and 1 way of doing that step, then the total number of possible ways of doing that operation is 3 times 4 times 6 times 2 times 1, and we can compute this, I guess. This here is equal to 24. 3 times 2 is 6, so 24 times 6, 24, that's equal to 24 times 6, and 24 times 6 is equal to 12 times 12 is equal to 144. Don't worry about the arithmetic. The arithmetic's wrong. Mice means ignore. Ignore that. This is not an arithmetic channel. Okay, so let's go to the first example question. How many different 3-course meals could you create from 3 starters, 5 mains, and 4 desserts? So as we said, if it's a k-step process, in this case, the operation is choosing a full 3-course meal, and there are 3 choices for the first step, as it were. The first step is choosing the starters, second step is choosing the mains, third step is choosing the desserts. So it's going to be 3 options for the first step, 5 options for the second step, 4 options for the last step. Then it's 3 times 5 times 4. That is 60 ways, or rather 60 different 3-course meals. I'm not going to write all that out. Yeah. On to the next example. How many different ways can you rearrange? How many different ways can the letters of the word water be rearranged? I just thought of a random 5-letter word because I don't want to go all the way up to like 6, or like, get 6. Anyway, okay. So you see, we have to choose 1, 2, 3, 4, 5 letters. You have to choose 5 letters. So the number of steps in the operation is going to be 5. Okay, that's the 5 steps. I don't know why I put that hyphen there. That hyphen with that dash. Hyphen dash F. It's a hyphen, yes. Sorry guys, I haven't done English in a while in school. Okay, so for the first step, you have 5 options. Oh, I should mention that none of the letters should be repeated. So for the first one, let's just write the word water here. You have 5 options. Then one of the 5 options is used up. Let's say it's W. Then you have 4 options left. Then you have 3 options left because you've used up the 4th one now. Sorry, you've used up a second one. So you have 3 left. Now there's 3. There's 2. There's 1 left. You see? So what this is called, in this case, there's going to be 5 times 4 times 3 times 2 times 1. That is 120. I don't know Actually, I know that off the top of my head just because I just know what 5 times 4. Okay, I just know. Anyways, so what this is also, this is known as a factorial. A factorial. A number multiplied, let's say some number n multiplied by n minus 1 multiplied by n minus 2 dot 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 all the way down to 1, that is equal to n factorial. So this number here is equal to 5 factorial. That is the factorials, introducing the concept of factorials. Yeah, and that's just like a shorthand way of writing all this, because this can be a lot. But okay, let's go on to another example, and then then we'll speak more on factorials and then the other applications of factorials. How many different 6-character passwords can be created from the lower case alphabet? How many different 6-character passwords? So in this case, let's say where repetitions are allowed. Let's say sub-question A, where repetitions are allowed. Where repetitions are allowed. So it's going to be 1, 2, 3, 4, 5, 6. So the reason I said lowercase alphabet is so that some people might not, so that there's no confusion as to whether it's uppercase and lowercase. Because if it was uppercase and lowercase, there would be a total of 52 characters to choose from. So here we eliminate all confusion. We just say the lowercase letters. So then it's 26. So for the first one, we have 26 options. And since repetitions are allowed, it's 26 again and 26 again, 26, 26, 26, right? And so by the multiplication rule, it's going to be 26 times 26 times 26 times 26 times 26 times 26, and that is just equal to 26 to the power of 6. Yeah, that is the answer for that one. And let's say there was another question where they said, where, I don't know if the English is correct, my bad guys, where repetitions are not allowed, so then there would still be 6 spaces, or not 6 spaces, but 6 steps. Yeah, let's call them 6 steps. And then the first one would still be 26, but now since that letter has been used, we can't use it again. So then there's only 25 remaining. Then in the next one, there's 24, then 23, then 22, then 21. I hope you guys understand that. It's just like with the water example where each time one of the letters was used up, so no, then we couldn't use it again. So we are left over with one less than the previous one. Then it's there, yeah. So this is equal to, therefore the total number of ways is 26 times 25 times 24 times 23 times 22 times 21. But this, as you can see, this is almost like a factorial, but divided by 20 factorial and lower. Or not 20 factorial, but divided by 20 factorial. It's the same thing. You may notice that. If you don't understand why that is, it's like you could say times 20 times dot 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 all the way until times 1. Let me rewrite it. Let me say equals to 26 times 25 times 24 times 23 times 22 times 21. I promise I'm going somewhere with this. I'm not just writing this all out just for just. I'm getting somewhere with my explanation. This is divided by 20 times 19 times dot 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 times 1. Because isn't it, these would cancel, so then that's why they equal. But we know that this part here is just 20 factorial, and then we know that this whole thing here would just be 26 factorial. So that would be 26 factorial over 20 factorial, and then that would be another way of writing it. And this brings us to permutations. Ignore this. So this brings us to permutations. So this is an example of a permutation. A permutation is used in a case where, firstly, things cannot be repeated, I think. No, not I think, yes. You use the permutation formula. I'll show you what the permutation formula is now. It's used when things cannot be repeated and when the order of the things matters. If you notice here, the orders of the letters of the password would matter, because if the orders were swapped around, it would create a different password. So the order matters, as opposed to if you just said choose letters and there was no order. If you just said how many different ways can you choose letters, then that would be a different thing, but we'll get to that. That's called combinations, and we'll get to that now, or maybe in a future video. The permutation formula is as follows. It's n. So this is the notation for permutation. The n is the total number that you can choose from. R is the number of steps or the available spaces, right? Like in that thing here where we had these lines, R would be 6, and then n would be 26, since you can choose from 26 letters, and they are R, in this case R is 6 spaces. So the formula goes as follows: n minus R factorial. And I'm not going to go into a proof of this formula. However, there is a proof. You can look into that yourself, or maybe I'll do the proof in a future video. I'll see about that, though. I'm mainly focused on the applications of these concepts, not so much on their proofs right now. As for right now, so let's try using this permutation formula on that same question. So it said we want to create a 6-letter password, and from 26 letters, so it's going to be 26 PR, R in this case is 6, is equal to 26 factorial over 26 minus 6, all factorial, that's equal to 20 factorial, 26 factorial. As you see, this is the exact same answer that we have over here, and as we've already shown, you can convert this answer into that, and vice versa. You can convert this into that. So that's basically like the basics of permutations. I think I'll also cover combinations. Combinations are the ones in which order does not matter. Let me cover a quick example of combinations. Let's say we have let's say we have a group of let's say you're playing basketball with your friends, right? You're playing basketball with your friends, and you have to choose a team. They say you can choose a team first, and you have to choose 5 players. You're not worried about players on the bench. You just will have to choose 5 players from let's say there's a group of 12 of you. That's why they can't worry about the bench. So if you want to choose 5 players from a group of 12, in this case the order does not matter. The order in which you choose them really does not matter. And so you could say you have 12 options here, 11 options here, 10 options here, 9 options here, and 8 options here. But then you're going to have to divide by 5 again, because you're trying to eliminate the possible different let's say orders, right? Because there are 5 different ways in which these numbers could then be ordered. Do you get me? That might be a little complicated. Sorry, not 5. Sorry, you have to divide it by 5 factorial, because there are 5 factorial different ways in which those numbers can be ordered. We showed that with the water example. You see, there were 5 factorials in ways in which you could arrange the 5 letters of water. So in order to negate basically the effect, or the remove altogether the number of different orders, you just divide it by 5, which is and 5 is the R. So let's just write the combination thing. So here, this is a symbol for combination. NR is equal to n factorial over r factorial times n minus r factorial. And you see this here is the division by 5 in this case, by 5 factorial. This removes the different orders. And this, as you can see, you may notice that this is exactly the same, right? As that. Okay, first let's say that just so that we don't lose anyone. Because to lose someone because of algebra would be a mistake on my part. Rather, just write everything out. You see that this is just NPR. This is just the permutation formula. That's just the oh, I hope you could see that. This is just the permutation formula, and then it's divided by r factorial. That's basically what we did there. So to actually get an answer for that one, let's quickly look at it. Let's quickly evaluate it. It's let's first try evaluating it without the formula, and then we'll use the formula. So you have 12 and you want to pick 5. So then it's 12 times 11 times 10 times 9 times 8. That's all over. Remember we said we want to divide by 5 factorial. But then this whole thing is 12 times 11 times 10 times 9 times 8 times 7 times 1 5 factorial, and then that's times 7 times times, I'm seeing times a lot, 1, and then these would cancel. That's why we can just do that, because it's the same as multiplying the whole thing by 1. And this is just the same as saying 12 factorial over 5 factorial. Oh my goodness, sorry, this is really getting messy. 12 factorial over 5 factorial times 7 factorial. Now let's try using this formula here. If I quickly just erase this, let's try using the formula. We say 12 choose 5. Oh, by the way, people often abbreviate it, not abbreviate, but a shorter way of saying it, instead of saying 12 combination 5, is people say 12 choose 5. Then you say 12 factorial over 5 factorial 12 minus 5 factorial, and then that's just equal to 5 factorial times 7 factorial over 12 factorial. I mean, not over, but 12 factorial over those things. And that, as you can see, is the same answer. It's the same answer. Again, there's a proof for this, but I'm not going to go into the proof. That's all for this video, guys. Please like, subscribe, and share the video. Thank you.